Hi everyone. I hope you can hear me well. And so we will start our presentation in a couple of minutes. I will open it. I will connect my iPad device, and then we will be ready. And I'm happy to see everyone of you right now. If you have some questions, maybe it's time to ask them now, because we kind of have some 1 or 2 minutes, especially if you have questions for Rodrigo, who is not busy with arranging the equipment. And I will be with you in 1 minute back.
Okay. Yes, I just want to say about that today we will also discuss during the seminar our projects that we'll be having today ready, and the whole mechanic, how it will work, what you should do over the next dates, and so on. And also we'll check the past 2 quizzes. There were some questions, so we can go through during the seminar through the answers and discuss what was expected and so on, so everyone understands. Some people were saying that they want to improve the results, so maybe through this explanation it becomes clearer to you what is necessary in order to get a good grade for the quiz.
Okay, I think I'm ready. I'm sorry for being a bit late, but I hope it was the best because some of your colleagues joined only recently. So I think it's kind of good things that we have like a couple of minutes gap between between the start of the meeting and the start of the lecture. So I think we are kind of ready. Happy to see all of you here one more time. And today we will cover another important topic in processing of sequential data that's related to embeddings of sequences. I think that most of you have some knowledge about this topic because they're quite popular not only for processing of sequences data, but we will cover them a bit, yes, but we will not go into details. But I hope that in the end you will have something that could be good for you and could be useful. And I suppose that you don't know everything from this lecture, even if you're like a second year master student. As any time, I'm happy if you ask me questions and give some feedback during the lecture because I feel a bit strange. Every day I read these lectures in Zoom. So let's start from maybe even more basic stuff. Let's see if we can do embeddings of categorical features and how can we do it. So, okay, maybe the simplest solution is to just have label encoding. So we have like our objects here, 1, 2, 3, so on. And so for each object, we know the value of a categorical variable. For example, we know that the first 2 objects are humans. Then we have a penguin, an octopus, alien, another octopus, and alien. And we can start with a mapping that maps each species to the particular number. So each human is 1, each penguin is 2, each octopus is 3, and so on. So in this way, we have kind of one feature that corresponds to this initial categorical feature, and it's pretty sure that we can map these numbers back to categories and that we kind of keep 100% information, especially if we don't know what the meaning, what each category means, and or don't care about it. And in this particular case, we see that we can even do good if we use something like gradient boosting, because for gradient boosting, we can distinguish between different numbers and say that for this particular number, we will have this particular classification or regression model answer. But for many more complex methods, this should not work, or it will not work as expected, because we don't have any natural order on these particular things. We can't say that humans are somehow better than penguins, penguins are better than octopus, considering the target function we are trying to approximate in this machine learning problem. So if we have something like logistic regression and we have like this feature x, and we include the term w multiplied by x in our sigmoid function, then we definitely not going to have great times most of the times. It's kind of weird feature with no particular reasoning for the ordering of these categories. So, okay, for a start and for random forests, it can work. But we don't have any interpretation, and we expect that in that it would be like MS if we apply something like logistic regression, and some features are generated using label encoding. Okay, we can go and use another approach, which also not a label encoding, but one-hot encoding. In this case, we just get multiple features from one feature, from one categorical features, and with number of categories k categories. We have kind of k minus 1 features, and each feature is a binary feature. And for each feature, we say that it equals to 1 if this particular object has this particular value of a category, and 0 otherwise. And for these particular examples, we can say that we have 2 humans, and so they have ones in for the feature is the human. The same for penguins, they are not definitely penguins, and so on. And as we can we can have like all 0 rows here, it means that the category of this particular object is the last one. So it's something alien that we don't fall into the first 3 categorical values. So it's like another one-to-one mapping, and we can say that for human we have particular mapping of features 0 or 1, 0, 0, for penguins 0, 1, 1, and so on. So we can go back from this representation to the initial values of categories. And in this case, these features can be useful for gradient boosting, for logistic regression, for whatever approach you would like to apply. Okay, take into account that it's not, okay, like it requires actually a lot of memory, because we have like, can have many categories like 100, 200, and so on. And you can imagine that we have a word associated with each object in our training sample. In this case, we have like 200,000 of features that you need to store in memory and learn coefficients, for example, of a logistic regression for these particular features. It's not sounds like a very good problem, something you can solve, but somehow it works. You can try logistic regression with these numerous features, get reasonable coefficients, and kind of good model in the end. Oh, okay, you can do even better if you think a bit about these particular categories, and for these categories, say that we are not interested in particular category, and let's merge some of them. For example, it can be the case where we have like many cities in our training sample, like Paris, Moscow, London, and we have many cities that are mentioned 1 or 2 times in our database. So we can merge all of the cities and, for example, replace the category of all these objects by the country or by some specific category other, and for this other we will have another 100. So it can work, and it require some manual decision making and manual selection of this hyperparameter on how large groups do you want to merge. But, and most of the time it's the best you can get for like category features for classic table data. There is many other encoders available that try to do a better job in encoding the categorical features. So they kind of represent each category with some numbers, so you can say it's kind of encoding. Many of them are based on the value of the target variable. For example, this is like some jargon name, categorical or likelihood feature. It is constructed in the following way. Let's suppose that we have like this categorical features, and we have two categories, 0 and 1. And we have values of the target function, like something like this. 7, 1, 1, 2, and 4. And we can encode these features using mean values of the target for each feature in our training sample. For example, we have two zeros. We see that we have two target values, 1 and 2. We calculate the mean value, it's 0.5. So our categorical encoding equals to 0.5 for this particular zeros. For ones, we can do the similar procedure. Let's slightly simplify my computations. And okay, so we again sum all these numbers and divide by the number of the ones in our training sample. So it would be 5 plus 7, 12 plus 16. Okay, it's 17 divided by 4, so it's 4.25. And so we have this encoding for our categorical features, and it kind of works good. And in many cases, we can improve from what we can do with something like one-hot encoding. Okay, and there's a lot more of them, and you can say that we can look even. Okay, if you're interested more in this topic, you can look at this benchmark, and you can see the comparison of all these the most popular encodings and how do they work in some settings. Actually it was like something like 15 datasets, but I can, I'm not sure about the exact number, but I'm sure about the order of magnitude of the number of problems they considered in this benchmark. So they were all classification problems, and for each problem they calculated Rockow score, and then they mapped this min-max scale of Rockow values to 0, 1, and then averaged the results for each encoder and present this guy in our table. And in the end, they have this validations. They have these numbers, and you can see that some of them works good, and some of that's not something you should try. That's kind of improves sometimes, not always the case. But if you have some tabular data, it's kind of a good idea to try some of them to be sure that you aren't missing something important, and because sometimes you can have drastic improvement on this time, but okay. And you can see that we have two settings here on the validation, on how we do the validation. So what it is about, it's about that we can use the same part of the sample to train the model parameters, to learn the model parameters, and to train this encoders, because as you can see from the example I already watered out from the slide, we use the actual target function values for many of these coders, actually. And you can see that in the first setting, we have no validation. In the second setting, we say that we use a separate training set to create encodings, and another one to use these encodings for training of the model. As we are suspicious due to possible problems with overfitting for this particular models, and so we can see that the ranking is a bit different. But again, in this particular case, this one-out encoder does not work out well. But okay, I think it's kind of hyperparameter. What kind of encoder do you apply? And you just apply all of them one by one until you get the result you want. Also, we have another option because, okay, we are mostly talking about neural networks. And because of this method is also can be useful, we can try to use neural network encoding. And what the idea of this neural network encoding is. Say that we map each category to a vector of numbers in this embedded space. So for humans, we have something like this. For penguins, another pair of numbers, and so on. So another one for octopuses, another one for lens, and so on. If we concatenate this encoding of categorical features with usual features like age or gender or education, and put all of them as input to our neural network, fully connected neural network, then we can use backpropagation to calculate the derivatives of the loss function in the end here when you compare the output of the neural network to true value. And so you can use gradient descent to learn not only the parameters of fully connected neural network, but also learn embeddings. So you optimize this vector to get the maximum performance, and it kind of work. And there are even libraries that can do it, but most of the time from our experiments we don't have much improvement over usage due to usage of neural networks instead of like another categorical encodings or no encodings at all. So it's kind of something that you, okay, similar to what I have in the previous slide. It's something that you can try, but it does not always work. Okay, we have a question here. What are the two values? We just optimize them like parameters of neural networks. So we suppose that, okay, we have for humans, yes, we will see later for encoding in time series data. So, okay, just wait maybe 10, 15 minutes and we will get to this part of my talk. About the question of Ilya. What we are doing actually, we say that for human, we have parameters theta1 and theta2. There are two parameters we want to estimate. For penguin, we say that it is theta3 and theta4. And so on. So we have, we concatenate all these parameters. We have these parameters that are related to embeddings. And we have parameters of neural networks here. Let's say that they are thetas with a third. And as in usual setting, we can say that we define a loss function for our training sample that depends on these parameters. So it, as you can see from the slide, the output of our neural network depends on the encoding. So we modify this theta2. We have different input to this neuron, and then you have the modified output, and so the loss function is different. So you can calculate the partial derivatives of this loss function with respect to not only the parameters of neural network. I hope you already know that for neural networks we can do it. It would be beneficial for the quality of it, but also we can do it for our embeddings, and we can use a gradient descent to say that our new values of embedded vector is something like old values minus like step size multiplied by the partial derivatives. And you can imagine that it's kind of similar to what we're doing with fully connected neural networks. You can treat the embeddings as additional parameters you train during the usual routine for training of any neural network. I hope it's clear now. Okay. Um, okay. Any more questions? Because we are moving to the part when we're working with actual sequential data. Okay, I hope no questions. So let's try to do it for sequential data and try to imagine why we should use something, why we should not use something. As in many other lectures, we have this kind of common example of what we should embed and what we should work with when we are thinking about sequential data. It is easy to understand and quite popular, so okay, I will start with like texts. And in this case, we can also use one-hot encoding. So we say that if we have this particular word in our sentence, that we mark it as one. And if we have like many words, here you count a number of occurrences of each word, and you have this future representation. It's similar to one-hot encoding, but with like multiple words, multiple similar words that can be in one sentence, so we can have not only ones but also two, three, whichever. And also, as we are thinking about this long vector, we apply something like logistic regression or random forest to have some prediction using this kind of input data. And it's surprising, but it can work quite well. And in some problems, this kind of approach is a very good baseline. It can work better than transformers, CNNs, recurrent neural networks, whatever you can imagine from the modern state of the art. If you just use this one-hot encoding to train this old guide logistic regression, then you get good results in the end. So, okay, it's really a good baseline. And also, as you can imagine, it's an example of an embedding of a sequence and an embedding of a particular token in the sequence. And so, okay, so let's move on and try something more advanced and more, maybe more related to modern science of recurrent neural networks. But at first, let's finish this part with TF-IDF. So let's imagine we have some kind of a set of documents, and we have, like, I'm sorry, another misprint. We have a token in this document, and we can calculate how many times each token appeared in a description of a document. And we have total number of documents and total number of documents that have the token T in it. And let's try to calculate TF value, term frequency. So we divide number of occurrences of a particular word in a document. So we fix the document and we fix the word by the total number of words in this document. So it's kind of the share of words that equal the share of tokens that equal to the particular token. Also, we can calculate inverse document frequency, IDF here, the second guy, and we say that it's logarithms of the total number of documents divided by a number of documents with a token tree. So if this number is small, then it means that almost all documents have this particular word or token. It means that likely we can't extract much from this word because it occurs almost everywhere. It can be like something like short word, like and, or maybe if you're thinking about money transactions, it can be some like getting your cash from ATM operation. I think that most of the people are doing this operation and we can't say much about it. Or most of people are going to grocery stores, supermarkets, and we can say what kind, is it a good client or a bad client on the basis of that he visits ATMs or supermarkets. And so if we multiply TF, okay, let's clarify a bit on term frequency. And we say that it's kind of weight of the word for this particular document. And so if we multiply this guy by this guy, we have TF-IDF feature that's defined for a particular word, for a particular document, if we have a collection of documents. So we replace these counters we had in a previous slide with these smart counters that take into account how frequent are particular tokens in our range of documents. And so we can say that instead we have the same number of features. Actually, we have like number of features that equals to number of distinct tokens in our data set. So it can be like hundreds of thousands tokens or thousands tokens if you have very large number of categories in our data. And we have like a lot of zeros as we had previously, because if we have no appearance of a particular word for a particular for a particular document, we have 0 here, and we have no zeros, and okay, something different. Then we have an accuracy of a word. Another good baseline, if you use this TF-IDF formulas, okay, I think they basically mean to be used for this logistic regression, because for logistic regression, it's harder to distinguish between unimportant and important features, and here we have kind of normalization here. And it has this basic intuition that rate tokens are more important because they have some meaning. It's not something that can occur in any text, but something that we can extract some information from. Okay. But okay, for very rare tokens, I suppose maybe it's not the case. Okay, so we tried to kind of introduce very basic barcode encoding and TF-IDF features. And basically they are embeddings too. If we look at them as very large vectors of features, and okay, maybe it's not a good idea to look at this particular embeddings if we are talking about the true nature of embeddings. We want something more advanced. We want the true representation that can capture some important features that are easy to calculate distances between and so on. And we know that we can do something like this for another structured data and by using of deep neural networks. If we have a figure and we process this figure through our layers of networks, and then in the end we have this fully connected layer and a representation of an object here. And we can say that these numbers are what we are looking for. They're really some kind of embedding of an image. So we extract representation from a complex object, and actually you can replace this like full connected layers, this kind of logistic regression layer if you have like only one layer after this embedding layer. This, for example, gradient boosting, and it works quite well, and these features can be used in many other settings. You can, for example, try to calculate distances between figures, and even if you use Euclidean distance, it can work quite good, and so on. So we have some evidence that we can try to learn embeddings for complex semi-structured data with neural networks. And we can try to do it for texts, for sequential data. We can say that we embed dates, operations, money transactions, and so on. And in this case, we say that it's easier to work with embeddings because they are like number, and with a number we can do our usual stuff in neural networks. And so we have this mapping between, we want to have a mapping between words or tokens and embeddings. I suppose a typical embedding dimensions are like between 200 and 1000, but it's another hyperparameter you can tune. If you're happy with what you have with your own sort of carefully selected dimensions, then it's okay. But typically it's something like this. So we want to learn this kind of representations of our tokens in like Euclidean space. And we can say that if we are doing well about this, we can try to use, for example, this kind of semantic similarity to judge if we are doing well or not. And in 2013, with word-to-vec embeddings, it was discovered that we can somehow relate different objects by the difference between them in the embedding space. So we say that we have these words, and we have for these words embeddings that belong to some, like in this case, two-dimensional space. And we can say that we can somehow relate these objects, and we can say that if 2 points are closer to each other, then maybe they have kind of close meanings for them. And if they far away, then there is nothing in common for this particular two words. And we can even say that if we subtract man from woman and on from uncle from aunt and king from queen, then we have approximately the same vectors. So we can say that if we learn embeddings well, we preserve the semantic meanings. And this is something we can check for tokens in natural language. But for sure, we can try to observe something like this for categories for money transactions, or maybe for months, and so on. It really works like a charm if you try to do this kind of work based on embedding objects. There are another couple of examples here. You can try to subtract capital from a country, and we say that these differences would be difficult, would be similar or very close to each other if we are talking about the similar relations between objects. And you can imagine even like this progressing of meanings for shortest, or similar triads of words. So we can try even check that we are doing the right thing in semantics. Okay, so there is actually a lot of ways to do embeddings. We will start with word-to-vec embeddings. They're quite popular in the past, and I suppose that these times most of researchers use additional approaches, but I think that it's important to know what was there before. Okay, so let's have some question for you. Okay, do you know what's word-to-vec? Can you print plus sign if you know and minus if you don't know? and maybe plus plus if you know how to program it at the moment. Okay, can you put a minus sign if you can't? Okay, at least we have some students who don't know what Word2Vec is, so I will have a brief overview of what is it, because, okay, as a hope, we can try to see what's the basic ideas of it. So let's say that we have kind of, okay. I don't think how this code is related to Word2Vec actually. Okay, but let's explain and see. Maybe I think about something different. So we want to maximize the likelihood of a sequence, and we want to say that this likelihood will depends on embeddings. And we say that the likelihood of a sequence or a sentence, if you're talking about NLP data, is something like this. So we have this, like the word or a token WT, and we have like kind of neighbor words, and we go using this sum by words, yeah, one to one. And we say that we want to, we want to see if we can generate a neighbor word using this word. So we can find, for example, likelihood that the next word is WT plus 1 if you know the word WT. And so for all words within a range defined by the constant C, and I suppose the typical value of C is something like 5. So it's the size of the neighborhood of how many words to each side of the word we are looking at. And we say that right now we want to estimate this likelihood using two embedding vectors. The first one is like for each word we have two embeddings. The first one with this prime is output embedding, and without it is input embedding. And we can calculate the embedding, this conditional probability or conditional density, as the softmax of the sum with respect to all words. So we see that here you have only embedding for this true word, and here you have embeddings on all words. Okay. So it's another heuristic. There definitely some kind of explanation of why it was introduced, but it's quite obvious that we can try to do the things, and maybe we will take something beautiful and interesting in the end. And so we can say that now, it's kind of works good, and we can learn good embeddings with words using these heuristics, and we can use these embeddings in many ways. There is another slide on how can we do a more interesting and but approximate way to calculate these embeddings, and we can see that we can kind of move out from this tedious task of calculating of these all softmax values. And we see that in the end, whatever way we use, we have good embeddings, and it was kind of state-of-the-art approach back there. But right now we can do better with, and it's an example of how can we do this kind of word-to-vec embedding. But we can do better if we try to do embeddings learned by recurrent neural networks. The thing is, we did the way similar to what we did. We go the way similar to the way we did when we were working with tabular data. We say that for each particular value of x, we will construct some embedding, and we optimize this embedding vector using backpropagation. So we backpropagate and get the partial derivatives and update our embeddings until we kind of converge. And this actually works fantastic. And actually, I don't know what kind of another things I can say about this particular slide. Just, okay, maybe it's the way I like most. And this is, we have specific layers to some embeddings in PyTorch and so on. What also an interesting thing to look at. It's about how can we use like one-hot encoding even for a sequence-to-sequence architecture. The thing is we need to output. Okay, suppose we have a translation from one language to another. In this particular setting, we say that we are interested in recovering this particular word. And we say that we need not embedding, but we need a softmax. So it kind of the recurrent, the RNN block returns the vectors of probabilities of each word. So it's actually return like 0.1, 0.11, and so on for each word we have in the dictionary. So we kind of train these particular probabilities, and we are okay even if the dictionary size is large and what the guys are actually doing. So it's kind of interesting to know that we have 100 encodings even if the coder for sequence-to-sequence modeling. So we recover this probability and select the best one, then use it as an output to input to the next block. We recover the second one in a similar way, and until the end, until we get to this end of sequence token or reach some limit in terms of that length of the generated sequence must be smaller than some kind of threshold. It's basically part of sequence-to-sequence recurrent neural networks, and they work like a charm. Even with RNN blocks, they can solve pretty tedious and complex tasks, and once they are state-of-the-art. And in many other problems, it still can do some work. I suppose it can be the case. So for word-to-vec, it works like a charm, and we don't need anything in between. But I can see that we see very small degradation of performance by using this hierarchical softmax instead of the true ones. So I think it's true story that we can use it for sort of sequence-to-sequence models. Maybe someone else can give more comments on this. And also, what interesting about this thing is that we can apply similar. Okay, let's miss it. I suppose it's quite similar to what we already have. And another thing that I want to conclude with is how can we do embeddings of sentences. We have obviously one obvious way. We just have a mean value of embeddings, or we have kind of pooling. So for example, we have like a number of embeddings for each word in a sequence or in a sentence, and we apply softmax, or we apply pooling, so we get, for example, maximum values for each component of the vector to get an embedding of a sequence. And this is a good and reasonable way to do embeddings for sequences. Also, we can do better. We can try to run a recurrent neural network. So we input these guys to some recurrent blocks and run this routine of training recurrent neural network, or LSTM. And so we have some kind of embeddings, this kind of hidden state in the end. It's also another way to embed a sentence. And actually we have a third way in between, which is depicted at the slide. It's like from this paper, it's very good and like easy baseline to try if you're trying to embed very long text. So you have some word embeddings for each word from some dictionary. You have a set of sentences. And we have parameter A and probabilities for each of the words calculated from very large corpus. And we can say that we want to get a sentence embeddings. Then for all sentences in our set of sentences, we just do this. We have a weighted sum of embeddings of each word, where we somehow normalize them by the probability of the word and some hyperparameter. So if we have more probable word, that it has less weight, and so we kind of adopt this TF-IDF routine to have a better embedding of a sentence. Also, we have a cherry on this cake. It means that we use this kind of first principle component of U. And for each, we have this modification of embeddings. So we kind of correlate this embeddings consequences. Then we can try to use it for some downstream tasks, and it works like a charm according to the authors of this article. But from what I have tried, it can work in many different settings quite good. I think that it's kind of why do we need embeddings of sentences? Because why do we subtract? Okay, I think that it is a way to decorrelate the different embeddings of sequences. So we try to subtract the joint part. And so, for example, okay, we kind of, if we imagine some kind of PCA for our data, and we have this kind of points, and we have this first principal component, we say it's not important because it's common for all embeddings we have. We want to have some distinct embeddings, so we decorrelate them, and so we have now embeddings that are more independent and easier to use and interpret, and they are more distinct if we look at different set of sentences. You're welcome, Mark. Okay, so I think it's a lot more on embeddings, but I think that I covered main points. And the main points for this particular line of research is that we can sometimes limit ourselves to simple methods like generation of embeddings for tokens by TF-IDF, and they can work sometimes as well as sophisticated neural networks like transformers or RNNs. Also, we can try to apply similar approaches when we embed very long sequences or sentences, or even sentences. Again, if you have some embeddings, for example, from Word2Vec, we can apply useless embeddings to have embeddings of large texts. Also, if you have neural networks, we can do end-to-end embedding training, and I think I like it very much, and it really works good. And also, I think it is at the core of this methodology of representation learning, because we directly learn what we need from what we want to get from the loss function, and also adjust embeddings remain meaningful. Also, there are many approaches to do embeddings like Word2Vec. I think that most of you know, for example, Glove. But I suppose in the era of transformers, they're a bit outdated, but okay, still can be useful for some tasks. And what we need to know, I suppose, is Word2Vec and Glove. And also you can see that most of these approaches are agnostic to the true nature of the data. You just have a categorical feature, and for this categorical feature, you train some kind of encoding or embedding, and it works well in many other areas. It works not only for NLP data. You can try it many times in many things. I think it is the end of the lecture, and I will spend the remaining time trying to explain the projects that are related to me. I will open the Notion page, and there you can see some 1 minute, and you will see what I'm talking about. If you have some questions about this embedding part, you can see it, you can ask them. But okay, I think you have no questions. And I can demonstrate to you also the projects I'm interested in. The first line of research is trying to kind of include some steganography based for recurrent neural networks. What is steganography? We try to like kind of hide information in text. Okay, so in text. And so we have the 3 parts. We have the text generator, information hiding algorithms, and information extraction algorithms. So we kind of publish text at our blog, and then like a secret agent from other country runs his information extraction algorithms, and he or she can extract some important piece of information from it. And for images, it's pretty easy actually. It's something similar to the serial attacks. You just modify a bit your image because you have a lot of information included in it. And so another user can extract this information. For NLP data and time series data, is more complex. So I think that it would be interesting project and interesting topic in general to how can we try to work on this topic and see how can we generate steganography linguistic frameworks using recurrent neural network. Another, yes, you can see the list of problems here. But also you can see that the last point of the research is something new, and so you will have a chance to bring some novelty to the scientific world of machine learning. But basically you can get the most for this project as well as many for other projects by replicating the paper. And also you can see that you have already have been distributed to different projects. So okay, let's move to the second one. Our second one is on how can we generate adversarial examples using generation models. Actually, it's maybe the most relevant to research project. One, and the idea is the following: we want to learn some kind of generation models like BERT or something else to generate adversarial examples that fool some particular model. So if you put this example in a black box, then for this black box outputs wrong output, wrong label for this guy. And so we will discuss in more details this kind of adversarial attacks, I suppose, in a couple of weeks. But okay, this is a project I want to propose. And the problem is that what we have already tried when we have pure BERT, we adapt it to generate adversarial examples for a particular sequence. But what I want to achieve in this project is to generate adversarial examples in a more general way. So we have all code, and in this case, the goal is to improve based on this code and to make something new you can contribute. And I hope that results can be good enough for publication here. Okay, Ilya, we will distribute you, and Rodrigo will assign you. Maybe as you haven't been listed, you have a freedom to choose a project. Okay, and the last one from me is how can we do unsupervised learning for sequential learning. And we have a very good paper on it. And so you will try to implement it. And what I also interested in is try to it on other data set. And that's okay. I hope that we will later discuss the exact data set. But either you have a chance to test it on kind of oil-driven data or money transactions data. I think whatever you will like more. Also, I don't have right now this oil and gas related data, so I suppose that the base scenario is try to use money transactions data. So it's all for my 3 projects, and I invite Rodrigo to start on the description of his own project and on the general timeline of how students will get the grade. So you're welcome, Rodrigo.
Yes, perfect. Thank you, Alexei. I will share my screen so then I can move it around. And yeah, 1 second. So